Alright, so let's solve the problems that require us to understand forces. Here in this problem, we will apply the concept of centripetal forces. So let's look at the question. The Ferris wheel at this carnival is at a radius has a radius of 12 meters. So I'll first draw a circle. That's my Ferris wheel, and its radius is given to me as 12 meters. A rider in this particular Ferris wheel, let's say my rider is at the top here. This person has a speedometer and they measure the speed to be a constant 4 meters per second. The first thing we are asked is to find the centripetal acceleration, the magnitude of the centripetal acceleration. Using the formula, we know that centripetal acceleration is v squared divided by r. Here v is, okay, I'll start with writing the known values. V is 4 meters squared, r is 12 meters. So to solve A, centripetal acceleration is v squared divided by r, which is 4 squared divided by 12. So 16 divided by 12 comes out to 1.33 meters per second square. So that's the acceleration. Now, if I have to find the amount of centripetal force in this particular situation, I'll just multiply the centripetal acceleration with mass. In this case, I don't know the mass, so this is my answer. And again, because we are asked the magnitude, I don't exactly need the direction, so this is just to show that that is the answer. Done. All right, so part B says that the rider's mass is 40 or 50 kg. If they check the weight on a weighing scale while riding the Ferris wheel, what is their weight? All right, let's understand what the question is asking us. If I have a person standing on a weighing scale, this person's mass downwards is W, and the amount of force applied by the weighing scale on this person is N. If this entire situation is stationary, N is equal to W. So when you stand on the weighing scale in your home, you're not moving and your home is not moving. So the amount of force you put on the weighing scale is equal to your weight. So the weight shown by scale is equal to W, which is technically equal to N. So the weighing scale can only show you the normal contact force it puts on you. It cannot show you your actual weight. In this situation, the person is not stationary. The person is moving. So if you remember in the lecture, I talked about how when your car is taking a left turn, when you're sitting inside it, you feel a force in the opposite direction of the turn. Similarly, this person in the Ferris wheel is going to feel a force in the opposite direction of the acceleration that the person is feeling, the Ferris wheel is feeling. So this person will have a weight downwards, a normal contact force N upwards. and he'll also be feeling another force, which is the force due to inertia, or the centrifugal force. Now we know that the magnitude of centrifugal force is just equal to the magnitude of centripetal force. Centripetal force is mass times acceleration, the centripetal acceleration. Mass is 50, and we know AC is 1.33. So this gives us 66.67 newtons. That's the centrifugal force. Now let's look at our free body diagram. Here we see that weight is downwards, so it's negative. The normal contact force is upwards, and the centrifugal force is also upwards. So performing summation of forces in the y direction, I have negative W, positive N, and positive Fi. And now this person, with respect to the weighing scale, is not moving. So the net acceleration inside the Ferris wheel, so if we are talking about inside the, let me call this the carriage, there is no acceleration. It's just like we are on Earth, and the Earth is moving, but we don't feel its movement because we are not moving with respect to Earth. So that's why the net force is equal to 0. So solving this, what we're trying to find is the value of N. N is equal to W minus Fi. Now W is 50 times 9.81 minus Fi is 66.67. So the value of N is 423.33 newtons. Now this is true for the situation in the figure. So at the top of the circle, at the bottom of the circle, if you perform the same, if you do the same particular math, your Fi, which is your centrifugal force, will be in the opposite direction. So your apparent weight, which is the weight shown by the scale, will be higher than the actual weight. This is very similar to the elevator, where if you're standing inside the elevator and the elevator is going upwards, you feel like you are getting heavier because you are feeling an inertial force in the downward direction. So this is your weight, and you're also feeling another force, which is the inertial force. So this is very similar to that situation. So the answer is 423. This question is the same question we solved in class today, but I'll resolve it again. First thing I know is theta is equal to 21.5 degrees. The road is curved, so if this is the road and this is the car, let's say it's moving in this direction, so it has a velocity in that direction. The magnitude of velocity, or the speed, is 19.8 meters per second, and there is no friction. Drawing the free body diagram here, That's the road, and my car lays on top of it. It has a force W downwards, and it has a force N, which is the normal contact force, upwards. So now because this particular car is going in a circle about a center somewhere around here, which is parallel, it's horizontal, so I'll just consider that my x-axis, and axis perpendicular to it, my y-axis. So now the normal contact force N is going to have an angle with both the axes. So I'll draw N. I don't exactly know the angle here, so let me calculate that. If this particular angle is theta, if this is 90 degrees, this should also be theta. So similarly, or just stretching that using trigonometry, I can say Nx is equal to N sine theta, and Ny is equal to N cosine theta. So performing summation of forces in the y direction, I get N cosine theta minus W is equal to 0, because the acceleration in the y direction is equal to 0. So N is equal to W divided by cosine theta. That's one equation. And then performing summation of forces in the x direction, I get, considering this direction as positive, N sine theta is equal to, now there has to be an acceleration in this direction, in the positive x direction, because the car is moving in a circle. This will be m times AC. So substituting the value of n, because we want to find out the radius of the curve, I'll substitute the value of n here. So I get W divided by cosine theta multiplied by sine theta is equal to MAC. W is mg, sine theta divided by cosine theta multiplied by m. AC is just v squared divided by r, dividing both sides by m. M gets cancelled, and now r is equal to v squared multiplied by cosine theta divided by sine theta divided by g. So calculating this, 19.8 squared I get something around 98 meters. So that's the answer. Going to the next problem. We are told that this particular leg is in a cast and it is supported in a traction device. This setup is called a traction device. And we are being asked to find the magnitude of force exerted by the leg, so this, on the small pulley. So let's break this problem down into multiple chunks. First things first, mass. If I draw the free body diagram for the mass, it has a weight pointing downwards and it's supported by the tension in the rope, so T. Now it's okay for me to assume that there is no acceleration here because this is a traction device and traction devices generally don't move. They support the weight of the leg and they keep it stationary. So performing summation of forces in the y direction, I have T minus mg is equal to 0. So tension in the string is just equal to the weight of the mass. I know the weight of the mass is 2.27 multiplied by 9.81, which is 22.27 newtons. So perfect. I know the value of T. Now, one thing I'll see here is that this is the same exact pulley, and here it's called T2. I called it T. So in the case of the pulley, T2 is equal to T. Now, because this entire string is the same, the tension in the string should be equal at every single point. So by that logic, I can say T1 is equal to T2 is equal to T. So at any point wherever T1 and T2 are involved, I'll just use T as the value. All right. So let's look at the pulley again now. So because I'm drawing the free body diagram for the pulley, because the pulley can move in x and y directions, I will just draw all the forces. The forces F towards the leg. There is a tension T and there is another tension T. Now it says T1 and T2, but we know that T1 is equal to T2 is equal to T. We know the angle between the axis that is created by the force F. We know the angle between that axis and the tensions. So what I will assume is that the axis on which the force F lies is my x direction, and a direction perpendicular to it is the y direction. So first thing I'll do is find the coefficients of T1 in the x and y direction. So drawing the triangle, this is T1, this is that, and this is 30 degrees. So the x component is just T1 cosine theta. So T1 cosine theta, which is equal to T times cosine 30, which is equal to 22. Actually, put the values in later. So T1y is T1 sine theta, which is equal to T sine 30. Doing the same thing to T2, we get that T2 is T2, the x component of T2 is T2 cosine theta, which is T cosine 30, and then the y component of T2 is T2 sine theta, which is T sine 30. Right, so these are the components. Now let's set up our equations. Forces in the x direction, there is negative F and then positive T1x and positive T2x. We don't know the value of F. Now one thing again we can be sure of is that the acceleration in the x direction is 0 because it's keeping the foot steady. so this will be 0. So F is just equal to T1x plus T2x, which is T cosine 30 plus T cosine 30 equal to 2 times T cosine 30, 22.27 multiplied by whatever is cosine 30. So my calculator tells me the value is 38.57 newtons. So that's the force applied by the magnitude of the force exerted by the leg on the small pulley.